Okay, so let's talk about coordination compounds. So what is a coordination compound? So in a coordination compound, it needs to contain at least one complex ion, which consists of a central metal cation bonded to molecules and or anions called ligands. So in a coordination compound, it has to have a complex ion, and then the complex ion contains a central metal cation bonded to molecules and or anions called ligands. Complex ion is associated with counter ions of opposite charge. So you can have a complex ion, and also if it is a positive complex ion, there should be a negative counter ion. If it is a negative complex ion, there should be a positive counter ions, opposite charge. The one that you are seeing here, complex ion, is chromium with 6 ammonium ligands. So chromium is a central metal ion, and then you have ligands 1, 2, 3, 4, 5, 6 ammonia, 6 ligands. Okay, NH3. The complex ion behaves like a polyatomic ion in solution. Remember the polyatomic ions like the carbonate, phosphate, sulfate, nitrate. So this complex ion behaves like a polyatomic ion in the solution. They are all going to be together, and then it dissociate from the counter ion. We can also come up with a coordination number, which is the number of ligand atoms bonded directly to the central metal ion. However many ligands are attached, that is going to be the coordination number. Coordination number is specific for a given metal ion in a particular oxidation state and compound. Now in this one, chromium with 6 ammonia ligands has a coordination number of 6. Most common numbers in complex ion is 6, 2 and 4. Most common is 6, but sometimes we will see 2 and 4 also. Components of a coordination compound. So here we have cobalt with 6 ammonia ligands and 3 chlorides, and this dissolves in water. When it dissolves in water like ionic compound, the 6 ligands remains bound to the complex ion, and then the chlorides will dissociate as the counter ion. Okay, and this is in solid form of this complex ion. And this you can see the written form, cobalt in the center, and these 6 are ammonia ligands in solid with 3 chloride anions. When you put it into water, they are going to dissociate into ions, and cobalt with the 6 ammonia ligands will stay as a complex ion, and the chloride will dissociate. So then this becomes 3 plus, and there are 3 chloride ions. Okay, same thing is written over here, showing you with the formulas. 6 ammonia ligands bound to cobalt chloride. This is the solid in water. This will remain intact. 6 ammonia ligands will stay intact with cobalt, and this would be 3 plus ion, and there are 3 chloride ions. Okay, and then here's another example, this one here. Potassium is the counter ion. It is positive ion is the counter uncomplex one, but the complex ion for platinum chloride PtCl4 is the complex anion. Here what you have is a complex cation and a simple anion, and this one you have a simple cation and a complex cation. So this is potassium in the solid form. It's all intact, platinum in the center, and then the 4 chloride ligands. When you draw it showing the ligands, so palladium is in the center, these are going to be your 4 chlorides, and then the potassium. Okay, coordination numbers and shapes of some complex ions. The geometry of a given complex ion depends both on the coordination number and the metal ion. So this is the coordination number 2. The shape is going to be linear because you have a central atom and 2 ligands attached to it. So these are some examples: copper chloride, silver-amine complex, and gold with 2 chlorides. And then when you have coordination number 4, there could be 2 forms. One is square planar, the other one is tetrahedral. So the square planar ones, you have metal atom at the center, nickel, and then 4 cyano groups, 1, 2, 3, 4. Another one, palladium with 4 chlorides, platinum with 4 ammonia, copper with 4 ammonia. All of these are square planar. And there could be some tetrahedral ligands or coordination compounds like copper cyanide, zinc ammonia complex, cadmium chloride, manganese chloride. So these are tetrahedral. And for the octahedral, where you have coordination number 6, you can have 6 ligands associated with the central atom. And these are some of the examples: titanium with 6 water molecules, vanadium with 6 cyano groups, chromium with 4 amine groups and 2 chlorides, manganese with 6 water molecules, iron with 6 chlorides, cobalt with 3 ethylene diamine. I will show you the structure of ethylene diamine. There are 2 coordination sites. So 2 times 3 will make it 6. Okay. So by looking at the formula, we can decide the coordination number also. Here 2, 2, 2, and then the 4. So this number, however many ligands they are, will tell us the coordination number. It doesn't have to be exactly the same type of coordination compounds like the ligands. Like in this case, there are 6 water, 6 cyano groups, but here you find 6 from 2 different ligands, 4 ammonia and 2 chlorides. 4 plus 2 is 6, like that. Okay. So the ligands of a complex ion are molecules or anions with one or more donor atoms. So these donor atoms are the ones that are going to attach to the central atom. Each donor atom donates a lone pair of electrons to the metal ion to form a covalent bond. Ligands are classified in terms of their number of donor atoms or teeth. Monodentate ligands bond through a single donor atom. Monodentate ligand, for example, let's say we have water. Water is H2O. So HOH. So there are 2 lone pairs, but it has only 1 atom. So this is called a monodentate ligand, bond through a single donor atom. Bidentate ligands have 2 donor atoms, each of which bonds to the metal ion. For example, ethylene glycol, like this. So this is CH2CH2. Okay, so this is OH. CH2, CH2, excuse me. I'm rewriting this one, CH2, CH2, and then you have OH group like that. So this can act as a ligand, but now it has 2 sites where it can bind. So we call it as a bidentate ligand. Okay, that's a bidentate ligand. Polydentate ligands have more than 2 donor atoms. You can have more than 2. Okay. And these are some common ligands in coordination compounds. So here are some examples of monodentate ones. Water with oxygen being the atom that coordinate. In ammonia, nitrogen, and fluoride, chloride, cyanide ion, it could be from carbon, and then thiocyanate ion. So the blue ones tells us which one that can be coordinated. So this is a linear molecule. In thiocyanate ion, either sulfur or nitrogen could use as the donating atom, but both cannot do at the same time because it's a linear molecule. So it's a monodentate ligand. Hydroxide ion, OH, oxygen is the donating atom. And then the nitrite ion, when you take the nitrite ion, it is oxygen, nitrogen, oxygen. There are two atoms that can be donated, but one at a time. So it's a monodentate ion. The bidentate ions are ethylene diamine. You see here ethylene diamine, this is the structure. So there are two nitrogen groups. Just like the OH I drew in the previous one, there are two amine groups. So these two, since it can bend the structure like this ethylene diamine, we give the formula En. Let's say you have cobalt here. So NH2 and CH2, CH2, NH2. H2N. So this nitrogen can coordinate like this. So it's a bidentate ligand. And if you have ammonia, NH3, it has only one side, it can coordinate like that. And the polydentate ligands are that you have more than two. So this one is diethylene triamine. There are three nitrogens in the molecule that can coordinate. And triphosphate ion, 1, 2, 3. Ethylene diamine tetraacetate ion, EDTA, that we did a titration also, one of your experiments. Ethylene diamine tetraacetate, EDTA, has how many donating sites? 1, 2, 3, 4, 5, 6 donor atoms. So they are polydentate ions. Chelates. So the bidentate and polydentate ligands give rise to rings in the complex ions like this. A complex ion excuse me, containing this type of structure is called a chelate, because the ligand seems to grab the metal ion like close, right? So EDTA, ethylene diamine tetraacetic acid, has 6 donor atoms and forms very stable complexes with metal ions. This is EDTA. This is the kind of complex that EDTA forms with calcium, magnesium when we were doing our water hardness experiment. Formulas of coordination compounds. Coordination compound may consist of a complex cation with a simple anionic counterion, or it could be a complex anion with simple cationic counterion, or complex cation with complex anion as counterions. When writing the formula for a coordination compound, the cation is written before the anion. Just like in our normal formula like sodium chloride, we always write cation first and then the anion. So in the coordination compounds also, we write the cation first and then the anion. The charge of the cations are balanced by the charge of the anions. It is the same way when we are writing the formula, like the sodium chloride. Sodium is +1, chloride -1. So the charges needed to be balanced. Like if you take magnesium chloride, magnesium is +2, chloride -2 when you have two chlorides. So we have to balance it. Neutral ligands are written before anionic ligands. So we will have neutral ligands and anionic ligands. So the neutral ligands like water, ammonia, so those are two neutral ligands. And then you have anionic ligands like the fluoride, chloride, cyanide. So when you are writing the formulas, hydroxide is an anion. What is the order? So we write neutral ligands before the anionic ligands. And the formula of the whole complex ion is placed in square brackets. So we put the whole complex ion in the square brackets. The charge of the cations are balanced by the charge of the anions. Now here you have potassium and then you have a square bracket. So what's inside is your complex ion. So potassium is outside. So potassium is a simple cation. So here you have a complex anion. Okay. The charge of the anion. So this charge of the anion should be balanced by the two potassium counter ions. So the anion therefore must be -2. Remember the cations and the anion should be balanced. So this is your cation, potassium. Each potassium is +1. So there are 2 potassium +2. So everything inside the complex ion should be then -2. There are 2 neutral ammonia ligands here. Okay. Now this slide shows you how to determine the charge of the metal ion in anions. Okay. There are 2 neutral ligands. So ammonia, you can refer to the chart I showed you. Ammonia is a neutral ligand. And chloride is -1. Right. 2 ammonia ligands and 4 chloride ligands. To have an overall charge of -2, now we're going to balance, we're going to find out what are the charges in each one of these. So ammonia is 0, 4 chlorides -2, and when you add up that with the cobalt, you see here, that will all equals to -2. Charge of the metal ion, which is -2, equals the charge of the complex ion minus the total charge of the ligands, to find out the charge of the metal ion. So the charge of the complex ion is -2, right? And then you subtract the total charge of the ligands. So ammonia 0. There are 2 ammonia ligands. There are 4 chlorides and then the charge is -1. So 2 times 0, 0. 4 times -1 is -4. So -2 minus -4 is +2. So the metal ion in this complex anion is cobalt 2+. That's how we find the charge of the metal ion in the anions. The procedure is you find out the ion, simple ion, and then opposite charge is going to be the complex anion, and then you find out which one are the neutral ones, which one has a different charge, and then you subtract the total charge of the ligands from the charge of the complex ion to find out the charge of the metal ion. Let's say you have a complex cation. How are we going to find out the charge of the metal ion? So this is chloride, and then you see a square complex in the square brackets. So you separate these two. So chloride is your simple anion and you have a complex cation. So Cl -1. Chloride is 1, so -1. So then the charge of the complex cation, this whole thing has to be +1. Charge of the cation balanced by the chloride counter ion. So the cation must be +1. And then you take the +1 and you subtract charges of the ligands. Minus ammonia is a neutral ligand, 4 times 0, plus chloride. There are 2 chlorides, 2 times -1. So this is 0. 2 times -1 is -1. Sorry, 2 times -1 is -2. -2 times -1 is +2. So +2 and +1 will give you 3+. So the metal ion in this complex cation is cobalt 3+. That's how you find the charge of the cation, metal cation. Okay. Give the coordination number and charge of the central metal ion in the following coordination compounds. First thing, we're going to see there are 2 sodiums here and zinc, and there are 4 hydroxides. What is the charge of sodium normally? Sodium is +1, right? There are two sodiums. So sodium is +1. There are two sodiums. So it's +2, this part. So then the zinc hydroxide, this whole thing equals -2. This thing is -2, right? So -2 is a complex ion, and you subtract zinc, we don't know, plus hydroxide, OH is -1, right? You can refer to this table over here to find out the charges. OH, hydroxide ion, OH -1. And this one is oxalate. We're going to be using this for the next question. Oxalate ion, this is the structure. 2 carbonyl groups and 2 oxygens like this, and it is -2 charge. And there are 2 coordination sites in the oxalate ion. So remember that, we need it for the next one. But we just look up for the hydroxide. For this one, zinc plus hydroxide. So there are 4 hydroxides. So 4 minus 1, -4, right? So -2 minus 4 times -1 is -4. So +4 minus 2 +2. So the zinc oxidation number for the zinc is +2, oxidation number. So or the charge of the central metal ion. So we just found out the charge of the central metal ion for zinc, +2. What about the coordination number? Coordination number is the number of ligands attached to it, the central atom, zinc. So there are 4 hydroxides, so it's going to be 4 going to be the coordination number, and +2 is the charge of the central metal ion. The next one, you have potassium and you have potassium, you have cobalt. So first we have to identify which one is the simple and the complex ion. So simple cation, and you have a complex anion, right? So the potassium is +1, therefore the complex anion is -1, right? -1, this whole thing is -1. -1 is this part, and potassium is +1. So to find out the coordination number, you're going to simply count how many things are attached to cobalt. There are 2 water molecules, and C2O4 is this structure, oxalate. Remember I showed you this one, OO. And there are 2 coordination sites in oxalate ion. That is these 2 oxygens. So each oxalate represent 2 coordinating sites because it's a bidentate ligand. So 2 coming from the oxalate, C2O4, and there are 2 of those. So 2 times 2. So each one has 2 coordination sites, and there are 2 of those. So 2 times 2 is 4. 4 comes from 2 oxalate ions, and there are 2 from here. So 4 plus 2 going to be 6. So the coordination number is 6. Okay. Coordination number is 6. Over here it also explains here. Potassium is the counter ion, so charge +1. Charge of the complex ion is -1. So the water ligands are neutral, and the 2 oxalate ligands have a total charge of -4. Because the oxalate ligand, I'll show you again. Oxalate ligand, this one, is charge is -2, C2O4. Okay, so this is C2O4. Ligand -2. When you see this one, charge of each one is -2, and this our complex, there are 2 ligands, so 2 times 2 is 6. So because of that, So negative 1 minus 0, and there are 2 of the negative 2 times 2 is negative 4, not 6, negative 4. So then negative 1 minus negative 4 plus minus will make it minus 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 plus, so plus 3. So the charge of the central metal ion is plus 3. So the next one, we have a complex cation. Here you have bromide, simple anion. Br is a negative ligand, bromide. So this whole thing is therefore positive 1. And let's see how many, what is the coordination number. Ruthenium is a central atom. So there are 2 water and 2 ammonia and 2 chloride. So 2, 4, 6. So the coordination number is 6. And then the charge of the ion would be, whole thing is plus 1. Water is neutral. Ammonia is also neutral. Chloride is negative 2. Negative 1 each one. So negative 2 would be 2. So the charge going to be therefore plus 1 minus 0, 0, negative 2. That will give you plus 3 as the charge of the central metal ion. Okay. All right.